Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to continue on our syllabus, chapter number 4, still under chi-squared test. So this is a last part of chi-squared test, which is a test of independence. Right, test of independence is used in research involved with two qualitative variables, right? Two qualitative variables. So basically, in a chi-squared test, we are dealing with the categorical variable, right? Two qualitative variable. So it will display data using a contingency table. Contingency table means that we have actually is a frequency table, but involved with two categorical data. So this is example of contingency table. This is a variable number 1. This is variable number 2. Let's say we have two variable, yes and no, yes and no. So inside is frequency value number 1, frequency value number 2, frequency value number 3, and number 4. And of course we have a total for row total. So this is what we call as a row total, and this is what we call as column total, right? And this is the last part is our grand total, the total of all frequency, right? So example of a test of independence, a professor is ranked by professional rank and the type of university at which she works, public or private. So of course in university we have a rank of professor 1, 2, 3 and 4, right? And then we have type of university, whether public or private. So these two variable are qualitative variable. So example number 2, a defective furniture is classified according to type of defect and the production shift during it was made. So this is an example of contingency table. So as I said just now, a contingency table have a row and column, right? So this is what we call as a row value, right? And this is a column, right? And this is the grand total, and this is the row total, and this is column total, provided this is a total, right? So contingency table has R row and C column, so that's why we call it as RC total cell. And we study relationship between two variables. So the objective of contingency table is we want to study the relationship between two variables, and these two variables are qualitative in nature, which is a categorical variable. So we want to know, is one method of classification contingency dependent or on the others, right? A chi-squared test of independence, right? So the hypothesis for a chi-squared test of independence, the null hypothesis is classification are independent, and alternative hypothesis, the classification are dependent, not independent, right? And then of course, if you are talking about a chi-squared test, right, the formula should be summation of observed frequency minus expected frequency squared divided by expected value, right? So this one, observed cell count are OIJ for row I and column J. Expected cell count are EIJ, which is NPIJ. Right, we will calculate the value of n multiplied with the probability of its row and column. If null hypothesis is true and the classification are independent, so the Pij should be Pi multiplied with Pj, right? So the expected frequency for a chi-square of a test of independence, right? The expected frequency is row total multiply with column total divided by the sample size, which is a grand total. This is a grand total, right? So it's very easy to calculate the expected frequency for a contingency table. Row total multiply with column total divided by the grand total, right? Now, test of independence. Let's look at the definition of test of independence, right? The test of independence involves a test of null hypothesis that two attributes of the population are not related. The degree of freedom for a test of independence are the number of row minus 1 multiplied with number of column minus 1. So this is the how we calculate the degree of freedom for a contingency table. Number of row minus 1 multiply with number of column minus 1. Right? The value of test statistics is a chi-squared value, right? For a test of independence. So the formula are same, right? Summation of observed frequency minus expected value, and then you square divided by the expected value, right? So this is the basic concept of test of independence. Right? We're going to use chi-squared test, chi-squared distribution, and then the degree of freedom is slightly different with the previous one, which is a goodness of fit. So the degree of freedom is number of row minus 1 multiply with number of column minus 1. Right, now to the step to do independent tests, right? So this is the step to do a hypothesis on independence test. So the first step is we need to state the hypothesis. Our null hypothesis is the classification are independent. The alternative hypothesis, the classification are dependent. And then the second step is we need to do a test value, which is we need to calculate the value of expected frequency for each cell. So we need to find the expected value, which is the row total multiply with column total divided by the grand total, right? So we will get the expected frequency for each cell, and then we're going to use the formula of a chi-square distribution. Observed frequency minus expected frequency squared divided by the expected frequency. If you have a 2 by 2 table, you can use the Yates correction, right? You can use a Yates correction, where the Yates correction is the modulus of expected minus observed minus expected minus with 0.5, and then you square divide by expected value, right? This is only for only applicable for 2 by 2 table, right? And then step number 3, we need to set a critical value, critical region, and then as usual, if you want to calculate the critical region, you need to have a degree of freedom for the chi-square. So the degree of freedom for the chi-square is row number of row minus 1 multiply with number of column minus 1. And then step number 4, we need to do a decision if the chi-square calculated is more than a chi-square value, then we will reject the null hypothesis. And the last step is we do a conclusion, whether the data is independent or dependent, right? So now let's look at example number 11, right? In example number 11, violence and lack of discipline has become major problem in school in the United States. A random sample of 300 adults was selected. They are asked if they favor giving more freedom to school teacher to punish students for violence and lack of discipline. And the two-way classification of response of this adult are present in the following table. So let me copy this table again for me to do a calculation, right? Wait, I think we start with the hypothesis first lah. The hypothesis, right? The hypothesis is null hypothesis. The classification is independent. The null hypothesis, the alternative hypothesis, which is HA, the classification is dependent. Right. So now let's assume our alpha is 0.05. So 0.05. We need to do a test statistic. Right. For the test statistics, we need to calculate the expected value of each cell. Right. So for the first cell, we have in favor, against, and no opinions, right? So this one should be our first column, in favor, and this is against, and this is no opinion. And the last one we have total here, and this one should we have man, and this is woman, and the last one is total, right? Let's do this way, right, for us to calculate the value. And the value of frequency inside each cell, favor man is 93. Let me put here 93. This is 70. This is 12. And this is 87. 32. This is 6. And the total for man is 175. And the total for woman is 125. The grand total is 300. The column the column total for in favor is 180. This is 102. This is 18, right? So now we need to calculate the expected frequency. The expected frequency, this is expected. Let me put the symbol only lah. This is E1, E2, right? So the expected frequency is, the formula for expected frequency, the row total multiply with column total divide by grand total, right? So the row total for man is 175, for in favor is 180. So 175 multiply with 180 divide by the grand total is 300. So this one should be equal to 105, right? Same goes to to against man, 175 multiply with 102, the column total, divide by 300, the grand total, which is equal to 59.5. And this one, same, 175 multiply with 18 divide by 300. This is equal to 10.50. We can continue to do this one. 125 multiply with 180 divide by 300 equal to 75.0. And then this one, 125 multiply with 102 divide by 300 equal to 42.50. And the last one is 125 multiply with 18 divided by 300 should be equal to 7.5. So now as we learned from the last class, the expected frequency, if you want to proceed with a Pearson chi-square test, the expected frequency should not less than 5. If you can see from the expected frequency here, none of the cell having expected frequency less than 5. So we can proceed with the calculation, right, to test the independence, right? So this is for this example, I just showing you how to calculate the expected frequency, right? So this is how we calculate the expected frequency lah. Now for the example number 12, right, let's do the rest, right? So reconsider the two-way classification table given in example number 11, right? So this is the same example lah. Example number 12 and example number 11 are the same, right? For example number 11, I just showing you how to calculate the expected frequency. So now, for example number 12, reconsider the two-way classification table in example number 11. In that example, a random sample of 300 adults was selected and they were asked in favor if they are favor giving more freedom to school teacher to punish the student for violence and lack of discipline. Based on the result of the survey, two-way classification table was prepared and presented in example number 11. This is example number 11. Does the sample provide sufficient information to conclude the two attributes, gender and opinion of adult are dependent, are related? So we are using 1% level of significance. So now this is how we do the hypothesis testing lah. This is a hypothesis statement, right? So the null hypothesis, again, gender and adult opinion of adult are independent, right? So alternative hypothesis, gender and opinion of adult are dependent. So our alpha here is 0.01, right? So now, since we already calculate the expected frequency, now the test statistic, right? Let me copy the table again. Oops. Try to paste here. Right. Right. So now the test statistics, we need to calculate the chi-squared. Calculated chi-squared is summation of observed frequency ij minus expected frequency squared divided by the expected frequency. So this one should be observed frequency, for the first cell, observed frequency 93 minus 105, and then we square here, divide by the expected frequency is 105. So this is for the first cell, right? Then we need to add up for the second, third and fourth until the last one. So the second one is 70 minus 1, the frequency, expected frequency is 59.5 minus 59.5 squared divided by 59.5. The last column for the first row is 12 minus 10.5 square divided by 10.5 plus for the second row 87 minus 75 square divided by 75 plus 32 minus 42.5 square divided by 42.5, and the last one is 6 minus 7.5 square divided by 7.5. So the value for the first one is 1.371, 1.853 plus 0.214 plus 1.920 plus 2.594 plus 0.3. So the value of chi-square calculated should be equal to 8.252, right? So now we already calculate the chi-square calculated. Step number 3, which is we need to calculate the critical region. Our critical region, we are using a chi-squared distribution, so the distribution curve should be skewed to the right curve, right? So now we are looking into 1%. Alpha is equal to 0.01. Our degree of freedom is R minus 1 multiplied with column minus 1. So number of row, so we have basically 1, 2 row. So we have 2 row, 2 minus 1 multiplied with number of column, we have 1, 2 and 3 column, right? So 3 minus 1. So this one should be 1 multiplied with 2 equal to 2. So our degree of freedom is equal to 2. The chi-squared 0.01 with 2 degree of freedom should be 9.21. So now our critical value is 9.21. Our critical value is 9.21. So then we can make our decision if chi-squared calculated is more than a chi-squared with 2 degree of freedom 0.01, null hypothesis is rejected. So since a chi-squared calculated is equal to 8.252, which is less than a chi-squared with 2 degree of freedom 0.01 alpha, 9.21, null hypothesis is accepted, right? So remember, this part is our rejection region, and this is acceptance region, right? So 8.252 is somewhere here, right? So then we can make our conclusion. Our conclusion is we fail to reject null hypothesis, right? We fail to reject null hypothesis, right? So we can conclude that gender and adult or opinion of adult are independent. So it does not related at all, right? So that's how we do a test of independence for this example, right? Right. Now let's look at the last example for this chapter. For the last example, example number 13, a researcher wanted to study the relationship between gender and owning cell phone, right? So she took a sample of 2,000 adults, right, and obtained the information given in the following table, right? So we have own a cell phone, do not own the cell phone, right? So at 5% level of significance, can you conclude that gender and owning a cell phone are related for the all adults? Now, our hypothesis statement. Null hypothesis, right? Gender and owning cell phone are independent or not related, right? Alternative hypothesis, gender and owning cell phone are dependent, means related, right? So our alpha is 0.05, right? This is the 5 level of significance. And then test statistic. So let me create a new table. For the test statistics, we have basically own cell phone and do not own cell phone, right? And this is a total, and we have man, which is gender, and woman, and the last one is total. Right, the value of frequency for men on the cell phone is 640. Do not own cell phone is 450. The total here should be 1090. Right, for women own cell phone is 440 and do not own cell phone is 470. The total should be 910. The total, the grand total should be equal to 2000. The column total for do not own handphone is 920. Column total for own handphone is 1080. Now, we should calculate the expected frequency. For man own cell phone is 1090 multiplied with 1080 divided by 2000. So this one should be equal to 588.60. For this one is 1090 multiplied with 920 divided by 2000 should be equal to 501.40, and this one should be 910 multiplied 1080 divided by 2000 equal to 491.40, and the last one 910 multiplied with 920 divided by 2000 should be equal to 418.60, right? So now we need to calculate for the chi-squared calculated. So chi-squared calculated, it should be summation of the observed frequency minus expected frequency squared divided by expected frequency. But if you can look at the table, right, we have a 2 by 2 table, means this 2 row and 2 columns. So what this is what we call as 2 by 2 table. If you look at the first example, we have 2 row and 3 column. So this is what we call 2 by 3 table, right? So now So if you have a 2 by 2 table, look at the notes that I give to you. For 2 by 2 table, we are going to use a rate correction statistics, which is we're going to take a modulus of observed minus expected minus 0.5 squared divided by the expected value. So the formula here should be changed to a rate correction formula. Right, this is only applicable for 2 by 2 table. So we're going to take the modulus of observed frequency minus expected frequency, right, minus 0.5 and then squared divided by the expected frequency. So the first one, it should be 640 minus 588.60, taking a modulus minus 0.5, and then we take a square here, divide by the expected frequency is 588.60, right? This is plus for everything. 450 minus 501.4, taking a modulus minus 0.5. This is minus 0.5 is a correction that Yates made for the Pearson correlation, Pearson's chi-square statistics. 501.40 plus the third one is 491 minus 440 minus 491.40 minus 0.5 squared divided by 491.40, and the last one is 470 minus 418.60, taking a modulus minus 0.5 squared divided by 418.60. So this one should lead us to 4.402 plus 5.167 plus 5.272 plus 6.189. So the total of a chi-square calculation should be 21.03. Right? So now the next thing is we need to calculate the critical value, critical region. Right? So we're still using a chi-square distribution, so the shape should be skewed to the right distribution, and we have a 5% error, 0.05. The degree of freedom is based on row minus 1 multiplied with column, number of column minus 1. So 2 minus 1 multiplied with 2 minus 1 should be equal to 1. The chi-squared with 1 degree of freedom, 0.05, is equal to 3.841. Right, so this is a 3.841. This is also called as chi-squared with 1 degree of freedom, 0.05. Right, and then we make a decision. Our decision is if a chi-squared calculated is more than a chi-squared with 1 degree of freedom, 0.05, null hypothesis is rejected. Right, so since our chi-squared calculated is equal to 21.03, right, 21.03, which is more than chi-squared with 1 degree of freedom, 0.05, which is 3.841, null hypothesis is rejected. So we can conclude, conclusion, right? Conclusion, we have a sufficient evidence. We have sufficient evidence that gender and owning a cell phone are related, right? So that's how we conclude our hypothesis. So I think by then we already complete our syllabus for chapter number 4. In chapter number 4, we already learned a chi-square test. First part, we have learned a goodness of fit test, and then we have learned a goodness of fit test to test whether the data is following the distribution, whether binomial distribution or Poisson distribution, right? And then the last part is we already look at how to test a test of independence. The test of independence is only for a categorical variable, right? I think that's all. For the exam, for the last homework, please make sure you do by yourself, right? If you have a question, please raise the question to me, and but before that, please discuss among you. If you all stuck, then come to me and ask me a question, right? Please comment. Please also leave a comment on the chat room below, right? If you have a question, right? So I think that's all. I think that's all, right? Thank you very much, and assalamualaikum.